In this video, I'll show you how to solve the ALEKS problem called Solving Limiting Reactant Problems in Solution. This problem has a 50-50 chance of being really complicated. So half the time this problem is going to be pretty straightforward, half the time this problem is going to be really hard. This particular variation of the problem is one of the straightforward ones, but I'm also going to show you how to tackle the problem if it was one of the harder versions. So as you can see with this problem, we are going to need to be consulting the solubility rules. I have taken a screenshot and pasted ALEKS's table of solubility, which just comes from ALEKS's data tab over here. You're going to want that. So in this problem, we have been given two different compounds. I have nickel to bromide, and I also have potassium carbonate, and the problem is asking us to calculate the molarity of one of the ions of one of those two original compounds. So I'm being asked to calculate the molarity of the bromide anion. And you're going to be asked to calculate the molarity of either the cation or the anion of one of these two compounds. Now, the thing that makes this problem tricky is that there is a potential for these two compounds to react with each other or interact with each other, which could have an effect on the molarity of the compound that ALEKS is asking us to solve for. Our first job is to figure out whether or not these two compounds will react. And if they do react, how will they react? And will that have an impact on the molarity of, for my problem, the molarity of the bromide anion? So initially with this problem, this is really just like a precipitation reaction problem, predicting the products of precipitation. So to do that, what we're going to do is start by writing a chemical equation, a potential chemical equation for the potential reaction that might occur between these two compounds. Nickel to bromide, the formula for that is NiBr2. I'm not going to go into details about how to write the formula from the name. This video is going to be long enough, and so I'm going to just focus on stuff that you need for solving this problem. If you don't know how to write the formulas of these compounds from their names, you can just look it up on the internet. Like you can just type in potassium carbonate formula and it's going to give you this, or you can look back at some of my other videos where I go over naming and how to come up with formulas from names. Now, our job, like I said, our job is to figure out whether or not these two things will react, whether or not they will form an insoluble solid. So again, this is a precipitation reaction type problem. And also, I'm not going to go into a lot of detail about predicting the products of precipitation reactions because, again, this video is going to be long enough as it is. If you don't know how to do precipitation reactions, then you will definitely want to go back and review that. If we're being asked to predict the products of precipitation reaction or determine whether or not these two things are going to react with each other, I think the easiest way to go about doing that is to take these ionic compounds and separate them into cations and anions. So that nickel Br2, I want to separate that into the nickel 2 plus cation and 2 bromide anions, and then the same with the potassium carbonate. I'm going to separate that into the 2 potassium ions and the carbonate anion. I'm leaving states off just to save space and save time. And again, one more time, if you don't know how to do this process, I'm not going to go over it in this video because the video is long enough as it is, but you can look back for videos on precipitation reactions, writing net ionic equations, things like that. That's where I go over how you would go about solving this part of the problem. So what we want to do, once we have these separated into cations and anions, we want to combine these cations and anions in new and exciting ways. We don't want to put the nickel cation back together with the bromide anion because that's what we started with. That's not new or exciting. We can't put the nickel with the potassium because they are both positively charged. So that means we need to put the nickel with the carbonate. That would be a formula of NiCO3. And we want to determine whether that is a solid, whether that is going to give us a chemical reaction. The other product of this reaction comes from the other two, the other cation and anion combining. That's going to be KBr. And again, we're trying to figure out what's going on with the nickel carbonate and the KBr. This is where the solubility rules come in, starting with NiCO3, using ALEKS's solubility rules. I want to find the nickel, it's right here, and carbonate is right here. With ALEKS's solubility table, no means no, it is not soluble, it is a solid. So that means this nickel NiCO3 is a solid, and in precipitation reactions there is at most one solid product, so I don't need to look up KBr. I know that it's going to be aqueous because once you have found one solid product, the other thing is not going to be solid. Okay, so we know that yes, these two will react. That's what we just figured out. Yes, they are going to react. The second thing that we have to ask ourselves then, once we've determined that they will react, is will that have an effect on the ion that ALEKS is asking me about? So ALEKS is asking me about the bromide anion. Is the bromide anion going to be affected by the formation of this nickel carbonate? Now, the way that we're going to figure that out is just like think about writing a net ionic equation. We don't really need to go through the whole entire process of writing a net ionic equation, but in a net ionic equation, we show only the formation of the solid products. We leave out the spectator ions, which are the ions that are forming the not solid product, the aqueous in this case. So our net ionic equation is going to look something like this. And we can see that the net ionic equation does not involve the bromide ion. The bromide ion is not involved in this chemical reaction at all, which means because the bromide is not involved, so I'm going to write this stuff down. Bromide, which is what we're trying to figure out, the bromide is not involved in the precipitation reaction. And this means that all of the bromide that we start with will be present at the end of this process. This, if you want to think about it as the reaction or the mixing or whatever, all of the bromide that we start with will be there at the end of the process. So to calculate the molarity of the bromide anion, we just need to figure out how much bromide we start with. When you have this outcome, so when this is your situation, this is the easier version of the problem. When ALEKS is asking you to solve for an anion that is not involved in the precipitation reaction, then you're happy because this is the easier version of the problem. ALEKS wants us to calculate the molarity of the bromide ion, which is going to be the moles of the bromide ion divided by the total volume of this solution in liters. Now, if we look back up at our data, we can see here's the volume. It is 200 milliliters, which is 0.2 liters, so we know that part. 0.2 liters. The moles of bromide are not given to us directly, but we have the mass of the nickel 2 bromide, and we can use that to figure out the moles of the bromide. So that's what we're going to do next. Now, while I'm writing this out, don't worry if you have the harder version of the problem. I am going to also show you how to do the harder version of the problem as well. So we've got 2.76 grams of NiBr2. What we want to do is figure out how many moles of bromide are in 2.76 grams of NiBr2. So our first job is to figure out how many moles of just that compound we have, how many moles of NiBr2 we have, and I went ahead and looked up the molecular weight of nickel 2 bromide earlier, so we have that handy, 218.5 grams per mole. Now this is going to tell us how many moles of nickel bromide we have, but what we actually need to know is not the number of moles of the NiBr2, right? That's not what we're looking for. We are looking for just the moles of bromide specifically. And looking at this molecular formula, we can see that we've got 2 moles of bromide in every NiBr2. So that's going to cancel out, and we can just use our calculator to work this out. 2.76 divided by 218.5. Oops, I hit the wrong button. Divided by 218.5 times 2 is 0.0253 moles of bromide. And we're going to plug that into our molarity calculation. And this is going to give us the molarity. And like I said, this is the easier version of the problem, and that even this version of the problem was pretty tricky. So the harder version of the problem, you can imagine, is going to be really complicated. So this is the answer to this particular version of the problem. And what I'm going to do now is show you the harder version of the problem. So to do that, I'm going to erase most of this. I'm not going to erase all of it because we're going to still use some of it. But I'm going to erase these calculations and this little conclusion that we came to. And I'm also going to reword the problem. So the harder version of this problem would be if ALEKS had asked me to calculate the final molarity of the nickel cation in the solution. This is a harder version of the problem because the nickel cation is involved in the formation of this precipitate, nickel carbonate. Okay, so if we are being asked to solve for the nickel cation, if the ion that we are being asked to solve for, if the ion is part of the formation of the precipitate, which nickel is, this is problematic because some of the nickel that we start with is going to be used to form this solid. Some of it is going to be left over and will be present in terms of calculating a molarity. So this makes this problem quite a bit harder. If the ion is part of the formation of the precipitate, then we need to figure out in order how many moles of the ion, I'm going to say nickel, I'm just going to keep it easy. How many moles of nickel do we have to begin? How many moles do we start with? And we also need to figure out how many moles of that nickel will react. In order to do that, we've got to figure out how many moles of carbonate we're starting with, because the carbonate is what the nickel is actually reacting with. So how many moles of the carbonate do we start with? And again, the reason why I'm choosing the carbonate is because the nickel and the carbonate are the two things that are reacting to form that solid. So I need to know how many moles of each one I start with, and then I need to figure out which of them is limiting. And let's just go there first. Let's just accomplish that first. Okay, so to figure out how many moles of nickel we have, we're going to basically do the same thing that we did at the end of the last version of the problem where we were right about to calculate the molarity. We're going to take the mass of the nickel 2 bromide, 2.76 grams of NiBr2. We're going to use the molecular weight, 218.5 grams per mole of NiBr2, and then we're going to use the molecular formula NiBr2 to convert from NiBr2 into just Ni. And for this one, it's a 1-to-1 conversion. So nothing is going on there mathematically, but it's an important step. And so let's just go ahead and do the math on that. 2.76 divided by 218.5. That is 0.0126 moles of nickel. So we figured out how many moles of nickel we have. Now we need to figure out how many moles of carbonate we have. And this one is going to be a little bit different and a little bit easier because for your other solution, you're being given a molarity and a volume. You're not being given a mass, so you don't have to do a gram per mole calculation. So my molarity of my other solution is 0.1 molar. That means that I have 0.1 molar means 0.1 moles per liter. And I'm going to move that over because it's hard to see. And that is moles of K2CO3. I'm going to multiply by my volume in liters. So I'm going to multiply by 0.2 liters. And that's going to give me moles of K2CO3. And then I'm going to convert that from moles of K2CO3 into moles of, what are we trying to figure out? Moles of carbonate. CO3, 2 minus, using the molecular formula. That also is just a 1-to-1 conversion, so nothing is happening mathematically, but again, it's an important step because sometimes it's not 1-to-1. So we do need to go through that step. So we're going to work the math out on this. That is 0.1 times 0.2 times 1 divided by 1 is 0.02 moles of CO3 2-. Okay, so step one, how many moles of nickel do we start with? We figured that out from the mass of the nickel. Step two, how many moles of carbonate do we start with? We figured that out from the molarity and the volume of carbonate. Now we need to figure out which is limiting. So let's go back to this. This is our equation that we're paying attention to, and I'm actually going to clean this equation up. It's easier to think about this if we're thinking about it in terms of the net ionic equation. So I'm going to erase this equation. We're not using that anymore. This is our total ionic equation-ish, and what I'm going to do is cancel out our spectator ions so that we can just take a look at the actual equation itself. Let's just erase those, get them out of the way. And this is our net ionic equation. This is the reaction that's happening. We need to figure out which of these two ions is limiting. We know that we have 0.0126 moles of the nickel and we have 0.02 moles of the carbonate. We can see from this equation that they react in a 1-to-1 ratio. That's not always going to be the case, but in this particular one it is. So we're looking for the reactant that's going to get used up first. The reactant that gets used up first is the one that we have the smallest quantity of because this is a 1-to-1 reaction. So my nickel is the limiting reactant. I'm just going to make a note of that. The nickel is the limiting reactant, meaning that it gets used up first. It gets used completely. That's what it means to be the limiting reactant. It gets completely used up. Now, if this problem was asking us what is the molarity of the nickel in the solution, it's kind of a trick question because all of that nickel ion is going to be completely used in this reaction. There is going to be no more nickel left. The molarity of the nickel is going to be 0 because it is the limiting reactant. It's going to be completely used. What I would like to do is, I got to erase a little bit here. So because that nickel ion is being completely used up, we're going to use all 0.0126 of it. When the reaction is done, there's going to be none left. So the molarity is 0. Now, what if this problem was asking us to calculate the molarity of the carbonate ion? If that was what we were being asked, we would be answering this problem a little bit differently because we would still go, if we were being asked about carbonate, we would still go through this same process. How many moles of nickel do we have? How many moles of carbonate do we have? Which one is the limiting? It's the nickel. And that would mean that the carbonate, because it's not limiting, some of it gets used up, but not all of it. When this reaction is over, we have a little bit of carbonate left over. And what I'm doing is taking my initial amount of carbonate, which I calculated, how many moles do I start with, and I'm figuring out how much of that carbonate reacts, which is, if you're familiar with ice tables, I'm just making kind of a generic ice table, but I'm saying I've got 0.0126 moles of nickel. That is how much carbonate is going to react. And when that reaction is done, I'm left with 0.0074 moles left. So this is my starting amount. This is how much reacted. And this is how much, 0.0074 is how much I have left. If the problem was asking me to calculate the molarity of my carbonate, I would then take that number of moles, the leftover moles of carbonate, I would divide it by the total volume of the solution, 0.02 liters, 200 milliliters, or 0.2 liters. My brain is getting fried. Oh, I see I wrote a 5 instead of a 4. My brain is really fried. This is a really tricky problem. The molarity of the carbonate would be 0.037. Now, you could get any one of the possible versions of this problem, so take your time working on this because there is so much work to be done. If you follow these steps, take really good notes, be really careful, you will get through this problem.